All right, so we are going to give this a shot and see if this is going to be working for us. So this particular topic is going to be on the physics of welding, which is pretty basic when it comes down to it. The physics of welding is you're melting something, it combines during the liquid phase, and then when it cools, you have a singular piece of material. So how do we do that is a little bit more complicated. We're going to get into that here in this particular presentation. Again, the definition of welding is this fabrication process whereby two or more parts are fused together by means of heat, pressure, or both, forming a joint as the parts cool. And essentially what that means, as it's pretty clear, I think, from the definition, you're getting something really, really hot until it gets to a liquid phase, so it's no longer a solid phase, that allows the two materials to combine with each other as they flow, and then once they've cooled, they form a stable joint, and then you have, it's not one new element or one new piece of metal, but it is a combination of those two, and they're fixed together in such a way that they won't pull apart. Ideally, they won't crack apart, depending on the skill level of the welder. Fusion of the two is the most typical way that we create this weld joint. Whether you are putting two separate metals together, ideally you're taking two parts and you're melting them until they become one in the middle, or you are choosing a third metal that you are then using to flow into each part respectively and creating a joint in the middle that will join those two pieces. So generally, high density heat is applied, and we're going to talk a little bit about heat density and power density here in a minute, and that ideally you want it to be a particular kind of heat at a very localized point is the best way really that we can do that. So high density heat is applied to those surfaces that are touching each other in order to create that joint. It causes the metals at those two adjoining surfaces to melt together, and then, as we just mentioned, join again as they cool. You want to, ideally, from an economic perspective, as well as the stability of your tool, you want to minimize the amount of heat that you have to use in order to perform this process. But you need to get it to a certain point depending on what materials you're using, or the process doesn't really work at all. But we're trying to avoid energy loss here. So talking about power density, it is defined as the power transferred to work per unit surface area, generally measured in watts per square meter, or in English system, BTUs per second square inches. Generally, some of the things that we have to think about are, if our power density is too low, then the heat just gets dispersed across the material itself, and so nothing melts. The conductivity of the material works against us, and then there's no melting. And if there's no melting, there's no flow, and so we don't actually get a welded joint. So if it goes too high, then your metals will vaporize, and then they sort of disperse into the atmosphere. They're not going to coalesce, they're not going to flow together, and they're never going to cool together, and therefore you, again, don't have a joint. So this Goldilocks region that we're talking about here is this liquid phase where the material itself is still localized, but it flows together and is able to intermingle and then cool together as one solid piece. This is the general power density equation. It is the power that you're putting into the surface in whatever system you're measuring that in, watts per square meter, millimeter, or BTUs per second. And then you have, BTUs per second or watts, and then you have your surface area over which that heat is being dispersed. So either in square inches or square millimeters. So it's a pretty simple equation in terms of how to measure power density. It's really not a calculation so much as it is just a measurement of what we're doing. These are some basic examples of our power densities. So oxyfuel, which is the thing that you would normally see, somebody has a torch. There's a little triangular flame coming out of, or conical flame coming out of the tip. And that's usually used to cut, though it can also be used to weld. Um, that's what you're going to be looking at when you see oxyfuel. Arc welding is when you are creating an electrical discharge, and that is creating heat over a very localized area. We have resistance welding, which is kind of similar to arc welding, but you're adding pressure to a very particular point in order to localize that heat over a smaller surface area, a much more localized surface area. And then laser beam and electron beam, which are a little bit more high-end, technologically advanced, where they're able to still have maybe lower heat, but to have it even over a smaller surface area. So your ratio is much higher because your surface area is reduced. Um, Here's some comparisons of different things, different ways of welding. So again, in the oxyfuel, the flame is spread over a very wide area. So while it's still very hot, you definitely don't want to put your hands on it. It's spread out over a very wide area, so you're losing a lot of heat to work. But your power density and your heat over the area is pretty low, as opposed to arc welding, which you're creating this electric discharge over a much smaller area. So while it may have a similar heat associated with it, it's over a much smaller area, and so that density is much higher. That power density that you're working with is much higher, even though the heat itself might not actually be that much higher. So then we have what's called the unit energy for melting, and this is leading a little bit more into whoever's going to be following me. They're going to talk a little bit more about how we use this unit energy for melting in terms of our calculations. But I wanted to go ahead and define it as the amount of energy required to melt a unit volume of metal. And so that's going to change from metal to metal, depending on the melting points of each metal. And so your energy is going to change based on the kind of stuff that you're working on. It is composed of these two different parts. The heat that is required to achieve the melting point, which again is going to change based on which kind of metal you're working with. And then your additional heat that is required to make that transformation from the solid phase to the liquid phase, because you can't just heat it to that point and then stop. You're going to keep heating so that it can retain enough heat to remain at this liquid phase, so that these metals will have time to intermingle and coalesce and then cool together. So that's where I will stop, and I will let whoever's moving on after this to finish. There's a little bit more to go in terms of the physics, but in terms of fairness and how things are split, this is where I will be finishing.